And here we get started on 5.6. We're analyzing logarithmic functions. Really what we're doing here is we're doing transformations of those logs. So now that reminds me, back years ago, they first did a pilot of the transformers there, and they made them out of wood. And they said, hey, this is a cool toy, all these wooden transformers, but the only problem is, it wasn't too difficult to defeat them. All you got to do is light them on fire. So the log transformers didn't go over very well. We also don't have to use a log table anymore. We've got it stored into our calculator for base 10. Now these logs here again are base 10. All of them. We don't have to show it when we use the common base, the common log, sorry, of which is base 10. So we can use our log button on these ones and punch it straight into our calculator. So you would just punch in log of 5. So log of 5 is equal to, and make sure you punch them into your calculator, make sure you get the punching in correct here, 0.6989 ... and then 2 log base 10 of 2. Punch that straight into the calculator as you see it. You should come up with 0.6020 ... Brackets on this one, very important. You got to make sure that you bracket those off and finish the bracket, especially on the numerator. You punch that into your calculator, 0.7924 ... There's only 2 bases that the calculator has stored. Base 10, because we got 10 fingers in our base 10 number system that we have. But there's also what's called a base E. That looks like garbage. There, base E. We have a log base E of, let's say, of 5. And we don't have to worry about base E in this course very much, but I am drawing your attention to it because it is used a lot in engineering and especially in calculus as well, where we use this number. E is not a variable. It's not like x. It's like pi. It is an irrational number that goes on and on forever. And we'll be using that in calculus a lot more. It's a naturally occurring number. E is. And so because of that, when we talk about base E log, we say that it's the natural log. We say that these base 10 are called the common log. And you've got that button actually on your calculator for the base E. It's the LN button. And that button's right below the log button on your calculator there. All other bases, we're going to have to take and move to either a log base E or a log base 10 in order to do it. I'm going to focus exclusively on the common log in this course here. Now, playing around with this question yourself kind of helps you to develop the strategy with this. Let's start with log base 2 is 6, and let's just make it equal to x. Well, let's solve it by taking it into exponential notation. So we've got 2, base stays as a base, 2 to the x is equal to 6. Now I can multiply 2 to both sides, it'll still be equal. I can add 4 to both sides, still be equal. I can square root both sides, still will be equal. As long as I do the same thing to both sides of an equation, it will always be equal. I'm going to take the log of both sides, and it will still be equal. So log of 2 to the x equals log of 6. Okay, we've got a rule that we can bring that exponent down for the logs. So now we've got x log of 2 equals log of 6. Log of 2. That is just some number. It is a special number. Just happens to go on and on and on forever. It's irrational. But it's just a number just like any other number. Log of 6, that's just a number. If I want to isolate my x now, I can just divide my log of 2 over to the other side. So it looks like x equals log of 6 divided by the log of 2. That I can punch into my calculator because I've got it now in base 10 logs, common logs. That's what I did here. I took the common log of both sides at the beginning. We can punch that into our calculator, and we come up with 2.5849 ... We can verify it by going back into our exponential part here, put the x in, and 2 to the 2.5849 ... gets us back to 6. So if we're going to be using our calculator, our technology, to be able to evaluate logarithms with bases other than 10, or e, but any other base, we're going to have to change it to a base 10 in order to be able to plug it into our calculator, because that's all that it's stored with. So first thing that we do, as you following the same process, we take it to exponential form. Then we log both sides. Apply our power law, bring that y down, and divide over the log b. Now with this one, we did the common log of both sides, log base 10. We could have done log base e of both sides. We could have done log base 5 of both sides. Not sure why we would want to, because we can't punch into our calculator, but we could do that. So the same pattern holds true with any change. So we don't have to go through that process all the time. We don't have to say, hey, let's start here, let's take it to exponential, and then work it down and down and down. That's a lot of work to get through for every single question. If we look at what our relationship is, if we're changing it to any base, so in this case, we're changing it to base A and base A, or usually you'll take it to base 10. You're going to take your x to go to the numerator, and the b to go to the denominator. So how are we going to remember which one goes where? Well, that b is slightly lower, so it's going to go to the bottom, to the denominator. The x is higher than the b, so it's going to go to the numerator. And now we only have one question for the Bitly link today. Which expression would you use now to change it to a base 2? Go in and vote that one for yourself. All right. Let's use our calculators. We're going to approximate the value of each, which really just means punch into your calculator, get it to a decimal, round your answer. And we're going to the nearest thousandth. And also write the related exponential expression to go with that. Well, log base 5, that's lower, of 50, is equal to. We're going to take it to a base 10 because that's what we can use in our calculator. So we've got log of something over log of something. And again, the 5 is a little bit lower, so it's going to go into the denominator. The 50 is a little bit higher, it's going to go into the numerator. And then we just punch that straight into the calculator. Log of 50 over log of 5. Make sure you can do it. That's approximately equal to 2.431 to the nearest thousandth. So 3 decimal places. 1,000 has 3 zeros. 1,000 has 3 decimal places. And give us the exponential expression of it. So what we're really saying is we're saying log base 5 of 50 is equal to 2.431. So then 5 to the 2.431 is equal to 50. exponential form. Okay, try that next one out. We take it. It's going to now be a log over a log. The 8 is lower, it goes denominator. The 6 is higher, it's going numerator. Punch it into your calculator. We get approximately equal to 0.862. And throw her down as an exponential. So then I'll just start with the log form first because it's easier to get to changing when you can see them all there. 8 is the base, so base stays as the base. So 0.862 equals 6. And you could punch that into your calculator just to make sure that it is pretty close to 6. Now, looking at the example number 1a in your book there, not the one we did, but in your book, log base 6 of 100 is equal to 2 over log of 6. Whoa, what's going on there? Where did the 2 even come from? I want you to work it through and come up with why that is true. Make that connection. And moving on to more fun now, let's use a graphing calculator to graph y equals log base 8 of x. Let's see what that looks like. So just remember that this should be the inverse of y equals 8 to the x. All right. Well, first thing, we got y equals log base 8 of x. We got to change it into something we can punch into our calculator. We cannot punch base 8 in. We got to change it to a base 10. So let's use that change of base formula, which is actually on your formula sheet. It's the fourth one of the logs, log laws there. So now we've got log of x over log of 8. Remember that the base is lower, it goes down to the denominator. Well, let's plug that in, and let's find, then we're going to identify the intercepts, the asymptote, domain and range. So let's graph it up. Okay, so log of x, and the bracket and your brackets, divided by log of 8, end bracket. Graph. Hey, we could zoom in there. Our window is, oh yeah, I got my window. Let's go to zoom standard. There we go. Let's graph that again. Perfect. So I can see it coming through there. Can't really see too much after the 1. Might want to zoom in a little bit more. I'm going to change my windows just so I can see it a bit better. I don't really need anything in the x-min, so I'm just going to go to negative, let's say 1. I don't need too much on there. I'm going to go to 5. Y minimum, you know what? I don't need much there as well. Let's go to negative 2. And let's go to 2. Let's see what that does. Oh, much easier to see. That's much better. So let's look at our intercepts now. Start with our x-intercept. Use our calculate feature. Let's find our 0. And go to left side. Come on, going slow. There we go, left side. Let's go to right side. Good enough. And let's find it in between there. Hey, it's at 1. You know what? We probably could have guessed that. So our x-intercept here is at 1, and we know that again because on the inverse, the y-intercept on an exponential would have been 1. So we've got an x-intercept now on this graph to be equal to 1. There was an asymptote on the original graph of the exponential, which would have been the x-axis. So now the y-axis is an asymptote. as we saw there in the graph. Okay, so you got your y-axis. It's going to be your asymptote. And the equation of that is x equals 0. Now, if that's an asymptote, that means there cannot be a y-intercept. So we're on to domain now, and range. Our domain, it's everything greater than that asymptote, or x greater than 0. And our range, we can have anything at this point, y, e, r. And those are just the inverses of your exponential. And now in comes everyone's favorite. We're looking at the transformations of these functions. We're going to take the graph and we're going to now move it. We got our stretches, we got our reflections, we've got our translations to look at. Everything's the same. This is exactly the same as y minus k equals cf of d bracket x minus h. Double bracketed on there. Exactly the same. The f, the function that we've been dealing with, is now just log base whatever. So that means we've got the k being our vertical translation. We've got the c being our vertical stretch by a factor of c. We've got our d, change colors, being our horizontal stretch by a factor of 1 over d. And then we've got our h, which is our horizontal translation, as you can see in the rest of that. We've also got that mapping notation, which is exactly the same mapping notation that we've used for any of the other chapters. Now, before we look at our number 3, we're going to get our guest speaker in. We flew this lady in to speak to you. Here she comes.
Part A. Create a table of values for y equals log base 3 of x. I'm going to start by writing the logarithmic function as an exponential function. Y equals log base 3 of x can be written as 3 to the power of y equals x. When y equals negative 2, x equals 3 to the power of negative 2, which is 1 over 3 to the power of 2, or 1/9. When y equals negative 1, x equals 3 to the power of negative 1, which is 1 over 3 to the power of 1, or 1/3. When y equals 0, x equals 3 to the power of 0, which is 1. When y equals 1, x equals 3 to the power of 1, which is 3. When y equals 2, x equals 3 to the power of 2, which is 9. Part B. How is the graph of y equals log base 3 of 2x plus 6 related to the graph of y equals log base 3 of x? Sketch these two graphs on the same grid. A point, xy, on the graph of y equals log base 3 of x corresponds to a point x divided by d plus h, c times y plus k, on the graph of y minus k equals c log base 3 of d times x minus h. I'll start by writing y equals log base 3 of 2x plus 6 as y equals log base 3 of 2 times x plus 3. Now I can compare the equation to y minus k equals c log base 3 of d times x minus h. I could rewrite the left side of the equation as y minus 0, so k is 0. This means that there is no vertical translation. I can write log base 3 of 2 times x plus 3 as 1 times log base 3 of 2 times x plus 3. So c is 1. This means that there is no vertical stretch or compression. D is 2, so there is a horizontal compression by a factor of 1/2. I can write x plus 3 as x minus negative 3, so h is negative 3. This means that there is a translation of 3 units left. A point, xy, on the graph of y equals log base 3 of x corresponds to the point x divided by 2 minus 3, y, on the graph of y equals log base 3 of 2 times x plus 3. So, the point 1/9 negative 2 on the graph of y equals log base 3 of x corresponds to the point 1/9 divided by 2 minus 3, negative 2, or negative 53 over 18, negative 2. The point 1/3 negative 1 corresponds to the point 1/3 divided by 2 minus 3, negative 1, or negative 17 over 6, negative 1. The point 1, 0 corresponds to the point 1 divided by 2 minus 3, 0, or negative 2.5, 0. The point 3, 1 corresponds to the point 3 divided by 2 minus 3, 1, or negative 1.5, 1. The point 9, 2 corresponds to the point 9 divided by 2 minus 3, 2, or 1.5, 2. I'll plot the points for the graph of y equals log base 3 of x first. 1/9, negative 2, 1/3, negative 1, 1, 0, 3, 1. 9, 2. Now I can join the points with a smooth curve for the graph of y equals log base 3 of x. Now I'll plot the points for the graph of y equals log base 3 of 2x plus 6. Negative 53 over 18, negative 2. Negative 17 over 6, negative 1. Negative 2.5, 0. Negative 1.5, 1. 1.5, 2. I'll join the points with a smooth curve for the graph of y equals log base 3 of 2x plus 6. Part C. Identify the intercepts and the equation of the asymptote of the graph of y equals log base 3 of 2x plus 6 and the domain and range of the function. First, I have to identify the intercepts. The x-intercept is negative 2.5. To find the y-intercept, I can substitute x equals 0 into the equation. So, y equals log base 3 of 6. Y equals log base 3 of 6 can be written as y equals log 6 divided by log 3. Log 6 divided by log 3 is approximately 1.6309. So, the y-intercept is approximately 1.6. The asymptote is here, so the equation of the asymptote is x equals negative 3. The domain of the function is all values of x greater than negative 3. The range of the function is all real values of y.
All right, let's try ours out here now. We're going to create a table of values for this original graph, log base 2 of x. Easiest way to do it, not the only way, but you could change it to exponential form. 2 to the y equals x. So let's choose some y values and see what x value comes with them. So let's take our x and our y, and let's choose some y values. Let's just choose negative 2, negative 1, 0, 1, 2. We can choose 3 as well. There we go. And let's plug it in. So we've got now, into the part here, 2 to the negative 2 equals x. So 2 to the negative 2, that is 1/4. So we've got 1/4. So instead of working the regular way on our table of values, we're selecting the y's, then we're finding the x's. Do the same thing with negative 1. 2 to the negative 1 equals 1/2. 2 to the 0 equals 1. 2 to the 1 equals 2. 2 to the 2 equals 4. And 2 to the 3 equals 8. Let's write those points right next to it for this. Let's go. So that's 1/4, negative 2, 1/2, negative 1, 1 and 0, 2 and 1, 4 and 2, 8 and 3. Now, how are these two graphs related? First thing, before you can start anything to do with transformations, you have to look. Do I have a double bracketed within? Okay. Well, there's only a 2x there. There's nothing that I can double bracket. That negative 1, that's outside. Really, there should be brackets like that. Log base 2 of 2x, then minus 1 at the end. And I'm going to bring the 1 over, so I've got y plus 1 equals log base 2 of 2x. I don't have to double bracket inside here, so we're good to go. Let's start looking at what our transformations are. Stretches, reflections. There is a stretch right here. So that's a horizontal stretch by a factor of 1/2. That was x being replaced with 2x. And that means in English, multiply all x values by 1/2. So we're going to do that to each point. We've also got the y plus 1 there. So that is a vertical translation, 1 unit, going y plus 1, so that's a y being replaced with y plus 1. Every single time you replace y with y plus 1 in that equation, it's translation, vertical translation, 1 unit down. In English, that means subtract, oops, let's spell that right, subtract 1 from y. So to the x, we're going to multiply by 1/2. That's going to give us 1/8. To the y, we're going to subtract 1. So that means we are now at negative 3. 1/8 comma negative 3. We've got the same thing. To the 1/2 on the next one, we're going to multiply by 1/2. That's going to give us 1/4. To the negative 1, we're going to subtract 1. That gives us negative 2. Continue that pattern all the way down. For each one of them, multiply the x by 1/2, subtract 1 from the y. Finish off those points. Okay, so there's the rest of your points. And let's plot them. And plot the original. See what that graph looks like. Then we start plotting the next one. This is quite interesting. I'm going to start highlighting from here. 1/4 negative 2. Ooh. Look at that. 1/2. That's quite interesting. When we graph both of those two, even though they are two different graphs, that's kind of like wacky. They are one on top of the other, what we call coincident graphs. Let's write that word down. Graphs are coincident. Means they turned out to be the same graphs. They coincide. But now we need to look at them and say, okay, where's the asymptote? And where's the intercepts? And the domain and range. So intercept. I'm actually going to do asymptote first. our asymptote is going to be that y-axis. So right through here, the y-axis, the equation of that is x equals 0. So your asymptote, x equals 0. Your intercepts now. There can't be a y-intercept because that's an asymptote, but we do have an x-intercept, and you can see it right there at x equals 1. Domain. Your domain is anything greater than your asymptote line, which is 0. So you've got x greater than 0, and your range, hey, it could be anything. It's y-e-r. Now the two different things that we did this lesson is we first looked at how to change the base, but we can use the calculator log button. And the second thing we looked at was those transformers. So answer those two questions up for yourself.